we'll do now is to take a few steps back to not look at individual new machines, but to get a broader view of the computer industry at this time, from early 60s to late 70s and early 80s. Okay, so Burroughs, one of the seven dwarfs, had released the first multi-core machine. And it was called a multiprocessor, and it had 4 CPUs and 16 memory modules. It was symmetric, which in this case means that every CPU could access every memory module. And the operating system had a shared queue of tasks that are ready to be executed on one of the CPUs. Okay, except for cache memories, this looks like a very modern machine. With today's standards, it would be extremely slow, of course, due to the CPU clock frequency, but since it has no cache. And as we will see, it turned out that this simple design, if we add caches and a suitable way to control them so that every CPU can get the same view of all variables, then that's probably the best way to make a easily programmable fast machine. Okay, what was also around at this time was the Multics operating system. AT&T, General Electric and MIT set out to build an operating system which would be a utility such as a telephone or electricity. You should just get the computer from the plug. And this was very not so fast hardware, and it would serve, that was the plan, approximately 100,000 customers in the Boston area. Okay, it was a big failure, but from it iPhone and Android phones originate in some sense. Namely, the engineers who wrote this Multics, they started with Unix, which became Mac OS and Linux later on. So what have we got? Software is either COBOL for economy programs or Fortran for high performance programs. And optimizing compilers, they can parallelize and vectorize numerical codes, and they are good at vectorization, but not so good, and still are not, on parallelization. And the fastest supercomputers, they have a few CPUs plus vector instructions, and they are either from Japanese companies or from Cray. At this time, it was realized that software development is more expensive than hardware development. Well, realized it turned out to be this case at this time when the software got more complex. Okay, so what to do about that? Well, the computer industry and academia went in the direction of creating CPUs which they thought would help programming in high-level languages and have good performance. So, for instance, there were instructions to set up a stack frame, to evaluate a polynomial, and to copy memory from one array to another. All this may seem not so difficult to do, but it is very complicated to implement this in hardware in an efficient way when we have this virtual memory and translation look-aside buffers, so that the data might not be in RAM halfway through evaluating a polynomial or copying data. It became very complicated. But nevertheless, fancy instructions were selling features. So bad. CISC processors, that's an acronym not invented by the designers, but later on. And it stands for complex instruction set computer, as opposed to simpler ones, reduced instruction set computers. And the typical example of a CISC computer is Intel's architecture. Intel tried to get rid of it, but they failed in the Itanium processor. It was, in the end, it was sometimes called the Titanic instead. Okay, so now we come to another interesting person, and it's John Koch. He finished his PhD in mathematics, and then he worked for IBM from 1956 to 1992. That's quite a long time. And he worked on computer architecture and optimizing compilers. And he designed a new processor. He set up a group to design a faster computer without requiring any compatibility with older computers' instruction set. And this revolution was partly done at IBM, partly done at Stanford University, and partly done at Berkeley. Okay, and so what is so special about it? Well, the idea is that it has only simple instructions, because compilers typically only use simple instructions. It's very rare that an optimizing compiler can match some part of source code to a very complex instruction. So these complex instructions are more difficult to implement in hardware, and therefore slow down the clock frequency, and the compiler don't use them anyway. So they are just waste and make the program slower. So some well-known RISC CPUs or architectures are Power from IBM, and that's the machine that we will use. ARM, that everyone uses in their phone, and some happy in their new Apple laptops, MIPS and RISC-V. Okay, I will not spend too much time on this, but there is now a movement to have open source hardware, and one step is to have license-free architectures, and IBM has removed the license fee to use the Power instruction set architecture. ARM, their income is from license fees for when companies use their architecture. RISC-V is a completely open source design, and there seems to be a good future for this machine. Not machine, but the architecture. In my view, well, it doesn't matter very much, but I think Power is a very good architecture, and they have so extremely much competence in this architecture, how to make fast machines for customers who want to spend, who really need the performance, and the cost is not so important.